quiz number 2. In a flat corner with a 30-meter radius, this is not a banked corner, this is a flat corner, a car barely negotiates a turn. In other words, we're going to be right on the edge. How fast is it going? This is a job for a free body diagram, and what I recommended to you, Victor, was kind of a front view. I said, I draw the pavement, I put my axis of rotation there, I do a little arrow just so I can visualize what's going on, a little curly arrow, and then Mr. Dueck brings out his fine art skills and says the car is coming out of the page towards us. Victor, my friend, what are the forces acting on this car? Get the obvious one. I totally agree. What else? Good. What else? And we would say, what path is this car tracing out? And you would say, a circle. And I would say, which way must the net force be pointing? And you would say, and then we would say, so I know there's a force there. Do I call this FC? No, it doesn't show up on my free body diagram. We would scratch our head. And yes, say it again. What force is it? Good. And so we can say, friction is what's pushing us in a circle. Mu, I don't know the normal force, mg equals mv squared over r. Victor smiles as he realizes that cars and big trucks can go on the same roads. What are we trying to find? V. Now, I would have no problem also giving you v and asking you to find r. I would have no problem giving you v and r and saying what must mu be, what must the coefficient of friction be. All of these, as far as I'm concerned, are fair game. Okay? Everyone staring out there? We're good? You're back? All right. So v, I can do that. V is going to be mu ger square root. So it's going to be the square root of 0.655 times 9.8 times 30 0.655 times 9.8 times 30, square root of that. Y'all get 13.9 meters per second, is that right? If you got that, 3 out of 3. Otherwise, I would probably go something like 1 mark for this, half mark for that, 1 mark if I saw that, and a half mark for the answer. Something like that. Oh, I can see some of you are disappointed. I forgot to put Anne's name on the quiz. Sorry. Better now, Michael? Yeah, I figured so. Find the speed. Well, speed of the spider is 2 pi r over the period. Problem is, I don't know the period. They've given me the frequency, and they've told me that it's 88 revolutions per minute. I need to change this to revolutions per second. How am I going to do that? Something to do with a 60. Times or divide. Believe it or not, I'm going to use the unit conversion stuff that I taught my Physics 11s. I'm going to say to myself, well, I want minutes to cancel. I want seconds, and I know 1 minute is 60 seconds. Where is that 60, Colby? On the... So it means divide. I've never bothered memorizing which one is which. So it's going to be 88 divided by 60. And I get a frequency of 1.46 repeating. So the period is going to be 1 over the frequency. That's what's going to go there. By the way, I guess technically another equation would be 2 pi r times the frequency, because if you're dividing by the period and frequency are reciprocals, then multiplying by the frequency would give you the same dealio. So, but I'll take the reciprocal. It's going to be that. Is the period 0.6818 repeating? .681818181818181818181. So it's going to be 2 pi r is 0.19, 0.681 repeating, 2 times pi times 0.19 divided by answer button. Do you all get 1.75 meters per second? Maddie's smiling, so that's a good sign. And that seems about right for a record player. I think this is a record player-ish or something like that. I would give you probably 1 mark, half mark, half mark. Mu, 3 marks. You know what, Victor? I think it's exactly the same free body diagram as the car. And so in the interest of time, I'm not going to do the free body diagram right here. Instead, I'm just going to say friction is what's pushing us in a circle. Mu times the normal force. I don't know the normal force. Oh, but look. I know the force is the same size as the normal force equals mv squared over r. The mass cancels. Now they want me to find mu. Okay, I guess I'm going to say that first of all, I need more room. There we go. I think I can safely say that mu equals, is it v squared over g? I think. Okay. Mu is going to be 1.75 squared. You know I'm going to use my answer button there. Divided by 9.8 times 0.19. It's going to be this number squared divided by 9.8 times 0.19. Now, at first that creeped me out. I don't know, spiders have sticky feet, don't they? They can walk on ceilings upside down, yes? So I think they have a mu bigger than 1 because they can support their own weight plus more than their own weight. So do you get 1.65? Yeah. Units, there are none. If you got that right, 3 out of 3. Otherwise, I would probably go something like this. Half mark, half mark, half mark, half mark. I don't know, 1 mark for the answer. I'd do something silly like that. Oh, the gravitron, 7 marks. Is this the last question? Hey, it is. Cool. This is a job for a free body diagram. Now, the person on the gravitron, what were the forces acting on them? Get the obvious one. I think we had gravity down. When you're on the gravitron, do you slide down the wall? Do you slide up the wall? So the forces must be balanced. I'm not sure what force that was. When you're on the gravitron, which path are you tracing out? A circle. So I know there must be a force that way. Oh, this we said was the normal force, and this meant that this was friction. So I have this. Normal force is what's pushing me in a circle. Normal force equals m4 pi squared r over t squared. I don't know the normal force. And I can't say, oh, but look, because I don't have another force the same size pushing this way. But there is another equation, James. Friction is equal to mg. Mu times the normal force is equal to mg. And now that gives me an expression for the normal force. Apparently in this situation, the normal force is equal to mg over mu. And I can walk that over to here. I'll get mg over mu equals m4 pi squared r over t squared. Johnny, can little kids and grown-ups go on this ride? Yes. Why? Well, that's kind of cool. What did they ask me to find? Minimum safe radius. Divide by 4 pi squared and times the t squared, I think. So the minimum safe radius, if you were designing this ride, would be gt squared over 4 pi squared mu. I think, is that right, folks? I'm seeing people nodding. 9.8, 0.5, and 3.2. 3.2 squared. Oh, 0.5, did I say? 0.45. 4 pi squared times 0.45. 9.8 times 3.2 squared divided by bracket 4 pi squared times 0.45. Did you all get a radius of 5.65 meters? If you got that, 7 out of 7. Otherwise, let's see, how would I give out part marks here, Mr. Dueck? I would probably go 1, 2, 3, 4, 5. Yeah, I would go like this. 1 mark for that, 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 and 1 mark for the answer. Probably something like that. Can you give yourself a lovely score, please, out of 15, my angels? So last day, we looked at this lovely roller coaster application where we ended up with 2.5 times the radius being the minimum height, and then we looked at the number of G's. I really like this question, but I'm not going to put this particular question on your test. I think it might be on your next quiz, but I don't think I'm going to put it on the test. It's just lengthy, but it's really cool. This will be on your test, though, example 2. A toy plane is attached to a ceiling. You may have seen this in shopping centers outside little gift stores or something like that. Often it's a little helicopter. I've seen a flying pig. I've seen a toy plane where it's going around in a circle. We have a name for this. So it's a toy plane is attached to the ceiling using a string. It has a propeller which causes it to move in a circle. And this is the side view. If we ignore air resistance and the force from the propeller, which balance each other anyways, what's the best free body diagram for the plane? A, B, or C? Well, let's see if we can figure it out. What are the forces acting on this plane? Get the obvious one. William? Does that get rid of any wrong answers? No. What else? Tension, you say. Does that get rid of any wrong answers? Mm-hmm. What else? Is there anything else? Well, here's the question. Johnny, what path is this airplane tracing out? So where must the net force be pointing? Towards the center, inwards. And it's a horizontal circle, so there has to be a force pointing that way. The question is really then, by the way, I think A is wrong. This is that mythical force that people think that they're getting pushed out. The question is, can these two give us a force inwards? How? William said yes. Add them tip to tail, you say. Are you saying if I go mg plus tension, that is enough to give me a resultant force inwards, but I don't need that on my free body diagram? In fact, it's the same free body diagram as the banked corner. So correct answer, C. Explain why others are wrong. I think we just did. We just did. So example 3 says, redraw the force diagram and write force equations for this toy plane. We call this a conical pendulum. A pendulum is a mass on a string. A conical pendulum because it traces out a little upside down ice cream cone. Okay. Well, we said we have gravity down and tension. And although this is at an angle, this also is one of the times that we don't want to break this into components. Why not? Because our circle is horizontal. The same reason on the banked corner that we left it that way, because our circle is horizontal. So I'm going to add these tip to tail. If I do that, whenever I'm drawing vectors and adding them together, I always start with the easiest one first. So I always draw mg first. Tell me when to stop drawing tension. Stop? It's a while back? We're going to try this again. There's a little participation first thing in the morning. Tell me when to stop drawing tension. Thank you. How do I know? Because I know when I add these two together, the net force is pointing which way? Dead center. So here is FC. Here's the lovely right angle. I noticed that between tension and a vertical line, that's where theta is. It's between tension and a vertical line. Here's tension, here's the vertical line. You know what? That's where theta is. The same place it was actually quite conveniently, Victor, in our banked corner. I think it ended up down there too. And my argument is, in terms of the physics, the banked corner and the conical pendulum are identical. So you ready? One of these will be on your test. I will either be giving you a question about the banked corner, in which case there you're being asked to find either the speed limit or the radius, because friction canceled out. Or I'll be giving you a question involving this, and we're going to do a few right now. But let's do the equations. Let's label our trig tension, opposite, adjacent, or hypotenuse. What was that?
As hypotenuse.
What about mg?
That's the adjacent.
What about fc?
Opposite.
Okay, so if you need to write the word SOHCAHTOA out, you can. There's really three equations in here. Which equation relates those two? So one equation that pops out of here is tan theta equals Fc over mg. Another equation that pops out of here, what's the cosine equation? What's the cosine equation that pops out of here? What over what? James? Good. And what's the sine equation that pops out of here? Fc over tension. And depending on what they give me, I'll use whichever one of these. Usually, I know the mass and g, and so usually I'm using that one, but not always. Certainly, you could use this to find the tension if you knew the mass. Keep in mind, this tension is tension, not period. And this is, again, Mr. Dueck's messing up. So what can I ask you? A ball is swung in a horizontal circle, turn the page, and it completes a single rotation in 1.2 seconds. The cord makes an angle of 35 degrees, as shown below. Okay. Dylan, what does A want me to find? Centripetal acceleration. Well, AC equals, how did I know I'm going to go 4 pi squared r over t squared, Dylan? Gives you the period? Cool. Did it give me the radius? Is the radius 0.44? No. By the way, if this was multiple choice, I would have one where you used an R of 0.44. I think the radius is right there. Draw that in. How can I figure out the radius? Okay, William said use SOHCAHTOA. There's often going to be two triangles in your picture superimposed on each other. One will be the forces triangle from the free body diagram, but there's actually also the physical length of the rope triangle. So if I draw this, I have 0.44 r and 35 degrees. R, opposite, adjacent, or hypotenuse? Opposite? What about 0.44? Which trig function? So I know that sine of 35 equals R over 0.44. R is going to be 0.44 sine 35. William, I'm feeling lazy. I'm actually not even going to bother calculating that. Instead, I'm just going to stick that right into there and just do it once. So on my right into there and just do it once. So on my calculator for centripetal acceleration, I'm going to go 4 pi squared 0.44 sine 35. Dylan, what was the period? I've scrolled down. 1.2 squared. I mean, I could have crunched it on a separate line, but I thought about it and said, whatever. 4, and that way I'm not rounding off at all. 4 pi squared 0.44 sine 35, close off the sine, divided by 1.2 squared. I wonder if this will give me an error. Oh, no. And I get a centripetal acceleration of 6.92. Anyone else double check me? Yes? Meters per second squared. Direction towards the center. Towards the center. Cool. Michael, what's B want me to find? How? R over the period. And you're realizing you might want your formula sheet handy? Good call, Michael. No need to memorize this. So it's going to be 2 pi, again, 0.44 sine 35. I'm lazy. I may as well just do that. All over 1.2. 2 pi 0.44 sine 35. Some of you, by the way, might need to put a times sign between your pi symbol and a number. It varies from operating system to operating system. I know I can get away with it. Oh well. And I get 1.32 meters per second. Direction, tangent to the radius, perpendicular to the radius. All right, we didn't do actually any forces or free body diagram. Let's do one where we got to do some analysis here. So example 4. This object moves in a horizontal circle on the end of the string as shown. If the tension is 42 newtons, A, what's the net force on the object? And B, what's the period of revolution? I like this question, I like this question, I like this question. This would be a good example of a conical pendulum question. Mateo, how would I start this out? You know what this is a good job for? Darn right I'd start this out. Now how do I know? What's A asking me to find? Okay. So what are the forces acting on this, Mateo? Get the obvious one.
Gravity.
What else? What else? Nothing. Okay. By the way, the net force is the vector sum of these two. Okay. How will I add these together? Tip to tail. I think I'll draw it right here. I have mg down, and then this time tension goes up and to the right. Tension. Here is FC. And I notice, Mateo, that between tension and a vertical line is 18 degrees. Here's tension. Here's a vertical line. It must be 18 degrees. Where's the net force in this picture? Sorry? No. In this picture, which of those three is also the net force? Yes. Yeah. Okay. Good. Now, I'm not going to go 4 pi squared r over t or mv squared over r. I think I'm going to use the fact that I know that this is 42 newtons. That 42, Mateo, opposite, adjacent, or hypotenuse. What about FC? Okay, I'm going to do part A right here. Which trig function? Good. 18 equals opposite over adjacent. So I think that centripetal force, which is the net force because it's the winner minus loser equals FC, is going to be 42 sine 18. 42 sine 18. And I get 13.0, I think, if I round off properly. Yeah? No? Anyone? There we go. B. How do you think I'll find part B? Probably going to use part A. Because, Samira, what did we find in part A? The net force, which was also F what? And does centripetal force also have a period in it? So I think I'm going to go like this. Fc equals m4 pi squared r over t squared. I guess the other thing I could have done is instead of asking you to find the period, I could have asked you to find the speed, and you would have gone Fc equals mv squared over r. How am I going to get the period by itself? I think, Samira, am I going to times the t squared there, move the Fc there, and that would give me a t squared? How to get rid of a squared? Yeah. So if I'm hearing you correctly, you're telling me period is going to be m4 pi squared r over Fc square root. Is that right, I think? You can see the real problem with this question. Look up, folks. James, you too. This T and this T, not the same thing. Is it possible that if you got interrupted and you came back here later, you would go and stick a 42 in there because Mr. Dueck and his notation is terrible? Yes, don't do that. It's going to be, did they give me the mass, Samira? 3.5 for pi squared. Did they give me the radius? They did. Now, in the last question, we used trig to find the radius. If I wanted to make this a little bit tougher, I could have given you the length of the cable and also made you find the radius like we just did. It's an extra step. All over, I'm going to write 13.0, but you know I'm using my answer button there, right? 3.5 times 4 pi squared times 0.6 divided by answer button, square root of that, 2 point something, 2.53 seconds. Okay. That is the conical pendulum, and you'll see a few of these in your homework as well. Speaking of homework, then, number 1 is good. Number 3 is good. 4 is good. 5 is good. 6 is good. You can skip 7. You can also skip 8 and 9. You can skip 8 and nothing. Okay. 10 is good. And then for some reason there's a number 9 after that. This number 9 you're going to do. I need to change. You know what? The issue is that should be number 8. This 10 is good. 11, 12, 13, and I am going to do 14. That's it. You can also now start whittling. Oh no, I need to tell you on Wednesday which of the ultimate review questions, because a bunch of them have to do with gravity. Unless anybody's planning on starting the ultimate review in the next 2 days, then I can tell you which questions you can do right now if you want to. No? Okay. Pause for a second.